Hello, ladies and gentlemen. We're going to do the series Library of Love. You notice it changes all to K. It doesn't really matter. I just wanted to point that out. But you can certainly change them back to N if you want. But I at least wanted to look at it a little bit differently today. But all right, so we're going to go through each of these just so you know which ones they are. First of all, at A, this is a P series. And P is equal to 1. So I think you know that that diverges. Okay, this one is the same one, but it's alternating. So what ends up happening, it is alternating. It is decrease. A sub n plus 1 is less or equal to a sub n, and the limit as n goes to infinity of 1 over k equals 0. By the way, a sub n is 1 over k. So therefore, it converges by AST. So by the way, if it's alternating and it decreases to 0, it's going to converge by AST. So let's look at D. It's alternating. 1 over k is root k is decreasing, and it decreases to 0. So this converges. Okay. If you look at this one, let's go down to F. It is alternating. It's decreasing, and it eventually goes to 0. So this one also converges by what? AST. Just a couple thoughts on those. All right, so if you go back to C now, C is also a P series, and K is equal to a half, and as long as K is less than 1, it's going to diverge, so this diverges. This one converges, this one diverges, this one converges, this one converges. Okay. P is 2, so it converges. So since both of these converge, we say this converges absolutely. Okay? Since only one of these converges, okay, we are going to say that this converges conditionally. What condition must it have? It must be alternating. Okay? This one converges conditionally. What condition must it have to converge? It must be alternating. Okay? All right. So now let's go look over here. We'll do a few in this column. Okay. This is geometric. And in fact, R is 1. Well, in order for geometric to converge, it must be between -1 and 1. If you think about it, this is also 1 plus 1 plus 1 plus 1. So this must also diverge. Okay? All right. So if you look at J, J is intended to be a geometric series. Okay? Your first term, just so you know, would be BP. Your next one would be BP squared. Your next one would be BP cubed plus BP to the 4th. And by the way, because K is 1, that's your first term. Well, this is geometric, and this would only converge provided that P is between -1 and 1. So as long as P is between those two numbers, it would converge. It's just geometric using different letters. Okay? All right. So if you look at K here, so we're doing first the sine of pi over 4. Then it's the sine of 5 pi over 4. Yeah.
I'm sorry. Okay.
All right. I got a little interrupted, so I had to start over, or just going to put these together. All right. So the next one was sine of, well, once I go pi units around again, I'm at pi over 4. And then it'll be sine of pi over 4 again, or 5 pi over 4. So this is root 2 over 2. So if I do my little unit circle here, I'm going here and here. First is root 2 over 2, then it's negative root 2 over 2, then it's positive root 2 over 2, then it's negative root 2 over 2. Well, it's geometric. And R is equal to -1. So what does that mean? It diverges. Okay? All right, so if you look at this one, we're now doing it at, find the sine of pi over 2 and the sine of pi later, which is down here, and just going back and forth. So this is 1, this is negative 1, this is 1. You go back up there, down there, it's negative 1, plus 1. Well, it's geometric. And r is equal to negative 1. Well, it's not. It can't be. It has to be between negative 1 and 1. So therefore, it also diverges. Okay? All right. So now if we look at this one, this takes this one up here, and I'm going to square this one, cube this one, etc. So this is going to be the sine of pi over 4. Okay. Then it's going to be the sine of 5 pi over 4 squared. Then it's going to be the sine of pi over 4, and then we're going to cube that. And then it's going to be the sine of 5 pi over 4. We're going to take it to the fourth. So this is root 2 over 2. This is negative root 2 over 2 squared. This is root 2 over 2 cubed. And this is negative root 2 over 2 cubed, or to the fourth. So what am I doing? I am multiplying by negative root 2 over 2 each time. So r is equal to negative root 2 over 2, which is less than 1, so it converges. So it is also geometric. Okay? All right, so if we look at n, choice n here, yes, we switch back to n on a couple of these. So this one is, I just want to rewrite it because it may look a little bit more familiar. Is if I do it 5 times 1, negative 1/6 to the n, that is exactly the same thing. That is geometric. And r is negative 1/6, so therefore it must converge. Okay? All right. Let's go down and let's go, jump back over here and let's go do h. Okay, so this is alternating. Okay, so we're going to use AST real quickly on this one. If you look at each term, we're looking at 2n over n squared minus 4. And as n gets bigger, as n increases, the bottom is going to grow faster. So initially it may not be true, but a sub n plus 1 is less than or equal to a sub n at some point, which is really what matters. Because when n is 2, I think I get undefined. Yeah, it starts at 3. So you get 6 over 5. Then you'd get, when n is 4, you'd get 8 over 60 minus 4 is 12. Then you would get 10 over 21, and each term is now starting to get smaller and smaller, so it's decreasing, and the limit as n goes to infinity of 2n over n squared minus 4 equals 0, so it converges by AST. Okay? All right, we got 2 left. Well, this one is not alternating. So I got to think about what can I compare it to. Limit comparison is our valuable tool here. Because this is not a p-series because I'm adding 4. So if I cover this up, 5 over n cubed is really close to 1 over n squared. Because that really, if you think about it, it simplifies to about 5 over n squared. So what we're going to do is we're going to use limit comparison, and we're going to compare it to just 1 over n squared, which we know converges. So we're essentially going to look at the ratio of the original one, which is 5n over n cubed plus 4 divided by 1 over n squared. You always divide by the one you know from our library above. So I get the limit as n goes to infinity, and I get 5n cubed over n cubed plus 4, and that equals 5. The key on this one is that that limit is finite and positive. So since this is finite and positive, it has the same behavior as this, which converges, so we're going to say it converges like 1 over n squared. Okay? If we compared something to 1 over n and it converged, we'd say finite and positive, and it diverges like 1 over n squared, because this will prove both. Okay, our last one on the page is the natural log of k over k. But the key here is it's alternating. Okay, so we're going to use AST because it's alternating. So the first one is a sub n plus 1 less than or equal to a sub n for the natural log of k divided by k. Well, as k increases, the natural log of k is always smaller than k. K is going to grow faster than the natural log of it. Okay? So what does that mean? Is it is decreasing, okay, because k is always bigger than the natural log of k, and they actually start to grow apart. Okay? And the third thing you got to test, remember, is the limit as k goes to infinity of the natural log of k divided by k does in fact equal 0, so therefore it converges by AST. Okay? So diverges, converges, conditionally convergent. What condition? Must be alternating. Diverges, converges, so again, it's conditionally convergent because only the alternating one does converge. Okay, when you get down here, they both converge, so this is absolutely convergent. So these were conditionally. Okay, got over here, this diverges because it really is geometric and R is 1, so it has to diverge. Here, this is geometric if you write out the terms. And the only way this would converge is as long as P is between -1 and 1. This one, if you look at it, if you map them out, it's geometric and R is 1, so it has to diverge, just like this one. The minute I put a power on this, now you looked at R is it's not just -1, is since you're squaring it, you're actually multiplying by -√2 over 2, which is the absolute value of that is less than 1, so it converges. This one, if I rewrite it, it is geometric, so it converges. This one we showed converges by AST. This one we showed it was an alternating, it converges. And this one we used, I didn't say by, I'm sorry, LCT, which is limit comparison test. Okay, you're comparing the limit of a known series which either converges or diverges. We use converges in this case. Just like if I would have had 1 over n plus 3, if that would have been our series from, say, 1 to infinity, this is a lot like 1 over n, which we know is a divergent p-series. So if I compared it to that, I did the limit as n goes to infinity of 1 over n plus 3 over 1 over n. Flip that up to the top, and I get the limit as n goes to infinity of n over n plus 3, which is 1. Well, it's finite and positive, so it has the same behavior as this one, so it converges, it diverges like 1 over n by the limit comparison test. Okay, there you go. Hope this helped. Bye-bye.